Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today we are starting a deep dive into diffraction from Unit 10, Wave Optics. Our mission is, well, it's quite simple, to explain this topic so clearly that you lose all fear and are fully prepared for the exams. Let's start with a simple question. You know that light travels in straight lines, right? That's why shadows are sharp.
Yes, that's the first thing we learned, the rectilinear propagation of light.
Exactly. But have you ever noticed the brilliant rainbow colors that appear when light reflects off a CD or a DVD?
Oh, yes, absolutely. Those shifting colors are so beautiful. But how is that possible? I always thought colors come from pigments, like in paint.
That's a great question. And this is where our usual idea of light traveling in perfectly straight lines uh, breaks down a little. Here's another surprising thing. If you look at a distant streetlight through the tiny gaps in your eyelashes, just squint a bit.
I've done that. You don't just see a single point of light, do you? You see these vertical streaks of light, sort of above and below the lamp.
You do. And that bending and spreading of light, which creates those streaks and the rainbow patterns where you'd expect just a sharp shadow or a plain reflection, that phenomenon is what we call diffraction.
Ah, so that's diffraction in action.
That is diffraction. Okay, let's unpack this. The core idea is simple. Diffraction is the spreading of light when it passes around a barrier or through a very small opening, like a slit or an aperture.
Okay, spreading of light. But why does it spread?
Because light is a wave. Think
Yeah.
of it like this. Imagine water waves approaching a narrow harbor entrance like a gate.
Right.
The waves, they can't just maintain their parallel structure when they hit that tiny gap. They're forced to bend.
So the gate acts like a new source, radiating waves in all directions into the harbor.
Exactly. We call this Huygens principle in action. Every point in that small opening acts as a source of what we call secondary wavelets. Now here is where it gets really interesting. These secondary wavelets, they overlap and they interfere with each other.
Interfere, like in the Young's double slit experiment.
Very similar, but with a key difference. Imagine the slit is divided into many, many tiny vertical strips, and each strip is a tiny, independent speaker broadcasting a sound wave.
Okay, like a wall of tiny speakers.
Precisely. The final pattern you see on the screen, the diffraction pattern, is simply the result of the sound from all those speakers interfering. This interference of wavelets from a continuous source, the slit itself, is what we define as diffraction.
I see. So diffraction is interference, but from a continuous source, not two separate points.
You've got it. That's the crucial distinction. Now, let us see how Ensert formally describes this, especially the result for a single narrow slit. Could you please read the condition for the minima, the dark regions, in the single slit pattern?
Of course. The Ensert document states, the minima, that is zero intensity, are at angles theta such that a sine theta is approximately equal to n lambda, where n is equal to plus minus 1, plus minus 2, plus minus 3, and so on.
Thank you. Now, that formula, a sin that equals nil, looks a bit intimidating. But let's break it down using our mental image of tiny sources. Here, A is the slit width, and O is the wavelength of light. Okay. Step 1. We're looking for the dark regions, the minima. This means we are looking for total cancellation or destructive interference. For the very first minimum, that's when n equals 1, we imagine dividing the slit into two equal halves.
A top half and a bottom half.
Yes. Now, step 2. If we consider a wavelet from the very top edge and another wavelet from the exact middle of the slit, what's the distance between them?
That would be half the slit width, so a by 2.
Correct. Now, if these two wavelets travel a path difference of up by 2, half a wavelength, what happens?
They'll cancel each other out. That's destructive interference.
Perfect. Now for the final step, step 3. This path difference of up by 2 between the top and middle wavelets is what gives us our formula. It means that for every single point in the top half, there is a corresponding point in the bottom half exactly up by 2 away.
That cancels it out perfectly. It's like every wavelet has a partner that destroys it.
Precisely. And that complete systematic cancellation is why we get a dark fringe. And this logic is what leads to the condition a sin equals a sina for the first minimum. So the final pattern is a broad, very bright central maximum right at the center at theta equals 0, followed by alternating dark and much weaker bright regions. The intensity falls sharply as you move away from the center. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now let's quickly look at a simple example to see the scale of this spreading. Suppose we use a laser with wavelength, let's say lambda is 650 nanometers,
Okay, a red laser.
and we shine it through a single slit of width A equals 50 micrometers. The screen is placed D equals 2 meters away.
Right. So A is very small and D is quite large.
Yes, the angular position of the first minimum is given by sin equals or by A, if we plug in the numbers.
That would be 650 into 10 to the power minus 9 divided by 50 into 10 to the power minus 6.
And what does that work out to?
Let me see. 650 by 50 is 13. And the powers of 10 give 10 to the minus 3, so 0.013.
Exactly. Now, since the angle is very small, the position of the first minimum on the screen, let's call it y1, is approximately d times sin,
Okay, so that's 2 meters multiplied by 0.013.
which gives us,
0.026 centimeters.
wait, 2.6 centimeters. That's quite a distance. But the slit with A was only 50 micrometers. That's tiny. That is the entire point. The width of the central maximum is 2 times y1, which is 5.2 centimeters. The light has spread over a distance roughly 1,000 times larger than the opening itself.
Wow, so squeezing the light through a tiny hole makes the beam massively wider.
It does. And this phenomena of diffraction, especially the spreading, is what determines the resolution limit of every optical instrument, like microscopes and telescopes. It sets a practical limit on how close two objects can be before they just blur into one.
So it's a fundamental limit of physics, not just technology.
Absolutely. Now let's move on. There are a few concepts related to diffraction that frequently lead to mistakes in exams. We call these the silent killers.
Okay, I'm ready.
Misconception 1. Students often think a narrower slit produces a narrower beam. It's like a narrow flashlight beam. The reality is the complete opposite.
But if the opening is smaller, shouldn't less light spread out? That feels so intuitive.
It does feel intuitive, but remember our formula. The angular width is proportional to lambda over A. So a narrower slit, meaning a smaller A,
Creates a much wider diffraction pattern, a larger spread. I see, it's inversely proportional.
correct. It's a counterintuitive result that follows directly from the physics. Now, misconception 2. Many students confuse diffraction with refraction. The words sound similar and they both involve light bending.
Yes, that can be confusing under exam pressure.
So remember the difference. Refraction is the bending that happens when light crosses a boundary between two different media, like air and glass. It's because the speed changes.
And it follows Snell's law.
Right. Diffraction, on the other hand, is the spreading of light around an obstacle or through an aperture. It's governed by the wavelength, not a change in medium.
So, to put it simply, refraction is bending because speed changes, and diffraction is spreading because the wavelets interfere.
Precisely. That's a very good way to remember it. An excellent exam-safe distinction. Now, to really lock this in, let's use a catchy phrase. Narrow slit, wide pattern diffraction spreads light far. Just say it a couple of times to yourself.
Narrow slit, wide pattern.
Okay. And for a physical anchor, try this. Take your hand and hold two fingers very close together, creating a tiny slit. Now look at a light source through that gap.
Okay.
The narrower the gap you make, the wider the light spreads out on your retina. You'll see it blur. That is diffraction happening right there, in real time.
That's a great way to experience it directly.
It is. So let's summarize the 3 most crucial points about diffraction for your exams. 1. Diffraction is the spreading of light around an opening. It is explained by Huygens' principle, which treats the opening as a source of continuous wavelets that interfere with each other.
Okay, spreading due to wavelet interference.
2. For a single slit of width A, the dark fringes, or minima, are located where a sin 3 equals nu. And remember, the central maximum is always the brightest and broadest part of the pattern.
Got it. The formula for the dark spots.
And 3, the most important one to remember. The angular width of the diffraction pattern is inversely related to the slit size. A narrower slit produces a wider spread of light.
Narrow slit, wide pattern.
Exactly. Now, a final thought for you to explore. Because diffraction limits how much light can be focused, the resolution of every microscope and telescope, its ability to distinguish two very close objects, is ultimately set by the wavelength of the light being used.
So we can't just build better and better lenses forever.
No. This Way's property defines the physical limit of what we can see in the universe, no matter how good our technology gets. It's a fundamental boundary set by nature itself. To get maximum marks in 12 CBSE physics, chemistry, and maths, visit ProfSam.com. That is PROFSAM. Yes, PROFSAM.com. All the best for your studies.